the hidden layer, and the memory portal. Inside your Linux kernel is a set of tools so powerful, most developers are afraid to touch them. You think you know Linux because you can manipulate files or manage system packages, but that is just the superficial user space. Beneath the distribution UI lies a hidden layer of raw, unrestricted power features baked directly into the kernel that allow for extreme system manipulation. The absolute lowest level of this forbidden domain begins with dev, mem, and dev kmem. In standard operating systems, the kernel acts as a strict gatekeeper, isolating application memory to prevent unauthorized access. However, these two character device files provide a direct, unfiltered portal to the system's raw RAM and kernel virtual memory. If a user possesses root privileges and the kernel is compiled without strict restrictions, reading or writing to dev mem allows them to bypass the entire operating system architecture. By calculating precise memory offsets, an attacker can scan live RAM to extract plaintext credentials or inject code directly into running processes without touching the hard drive. It is the ultimate bypass of the OS file system, treating the entire physical memory landscape as one massive, editable text file. Process hijacking via kernel stalking. Once inside the system, manipulating independent applications requires a mechanism to intercept their execution flow mid-stride. This is where the kernel's built-in debugging framework, ptrace, transitions from a standard developer diagnostic tool into an aggressive instrument for process hijacking. The ptrace system call allows one process to attach itself to another, effectively turning the target into a puppet. Once attached, the tracing process can pause the target, read and write to its internal memory registers, and alter its execution path on the fly. Hackers exploit this architectural feature to perform runtime code injection. By targeting a legitimate, highly trusted process such as a running web browser or a background system daemon, a malicious script can force the target to allocate memory and load a completely separate, unauthorized shared library. Because the injected code executes from within the memory space of the trusted application, traditional security monitors see absolutely nothing out of the ordinary. It allows for the complete subversion of running software, silently turning legitimate system utilities against the user without altering a single byte of their original binaries on the disk. The kernel's internal spy, eBPF. For a long time, altering how the kernel handled core tasks meant writing complex code that could crash the entire machine. That boundary dissolved with the introduction of eBPF, or Extended Berkeley Packet Filter. Think of eBPF as a mini, hyper-optimized virtual machine that runs directly inside the kernel space. It allows users to execute sandbox programs at the lowest architectural level without modifying the core kernel source code or loading unstable external modules. While developers use it for network monitoring, it serves as the holy grail for next-generation rootkits and system spying. Because eBPF programs can hook into virtually any system call or kernel function, they can intercept data before the operating system even processes it. An eBPF program can silently log every single keystroke typed in a terminal, capture network packets before they reach the local firewall, or dynamically alter the output of system commands. If you type PS to look for a malicious process, a running eBPF program can intercept that request and scrub its own name from the list. It represents absolute, invisible observability and manipulation from inside the matrix. Phantom networks with TUN, TAP. Network manipulation usually requires physical hardware access or complex routing tables, but the Linux kernel contains a native feature that creates entirely simulated network infrastructures out of pure software. TUN and TAP virtual devices. Normally, when an application sends network traffic, the packets move through the kernel down to a physical Wi-Fi or Ethernet card. A TUN network layer, or TAP, data link layer device completely hijacks this pipeline. Instead of routing those packets to physical hardware, the kernel redirects the raw network traffic straight into a custom user space program. This allows a programmer to build entirely phantom network adapters that don't physically exist. By capturing this raw packet stream, you can analyze, modify, or completely forge network traffic on the fly before forwarding it along. It is the foundational technology behind secure virtual private networks, but in the context of extreme system manipulation, it allows for seamless man-in-the-middle attacks. A script can use these virtual interfaces to silently clone, manipulate, or inject fabricated data packets into local network streams, forcing the operating system to talk to ghosts. Overriding the brain. Sysctl overlords. Every fundamental rule governing how the Linux kernel manages memory, handles crashes, and routes data is controlled by live variables inside the proc sys directory. Known as the sysctl interface, this pseudo file system allows a user to alter the actual brain chemistry of a running operating system instantaneously without a reboot. By echoing precise values into these virtual files, you can disable fundamental security mechanisms designed to protect the system from exploitation. For example, tweaking kernel. Randomize, VA, space allows a user to shut down address space layout randomization entirely. ASLR is the core defense mechanism that randomizes where programs sit in memory to prevent buffer overflow attacks. Turning it off makes the system immediately vulnerable to classic memory exploits. Furthermore, manipulating files like kernel panic allows you to force immediate system reboots under specific crash conditions, which is a tactic used to clear forensic memory traces. By treating core operating system parameters as simple variables that can be rewritten with a basic echo command, sysctl grants total, immediate authority over the kernel's operational logic. Living in Ring 0, loadable kernel modules. User applications run in a restricted environment called Ring 3, where the kernel limits what they can see and touch. The ultimate goal of extreme system manipulation is escalating all the way down to Ring 0, the CPU's maximum privilege level, where the kernel itself resides. The native mechanism for doing this is through loadable kernel modules, or LKMs. These are compiled .co files that can be dynamically inserted directly into the running kernel using commands like insmod. Once an LKM is loaded, it becomes an inseparable part of the operating system's core engine. From this vantage point, there are no permissions or security boundaries. You own the hardware. Malicious LKMs, often called kernel mode rootkits, hijack the system call table. When an application asks the kernel to open a file or list a directory, the hooked system call routes through the LKM first. The module can then selectively hide specific files, processes, or network connections from the rest of the OS. Because the deception happens inside the core kernel itself, any security software running in user space is completely blind to the modification. The hardware emergency eject. Magic sysrq. When experimenting with deep kernel manipulation, the system will inevitably freeze, lock up, or enter a state of complete unresponsiveness. When the mouse stops moving and the terminal refuses to accept input, standard users pull the power plug, risking data corruption. However, the kernel includes a hardwired, low-level physical bypass known as the magic sysrq key. This feature is a dedicated code path baked directly into the keyboard driver at the lowest level of the kernel architecture. By holding down Alt plus sysrq and typing a specific sequence of letters, most famously REISUB, you send commands that bypass the entire user interface and window manager completely. The kernel processes these keystrokes directly from the keyboard hardware, even if the rest of the operating system is entirely deadlocked. This sequence forces the kernel to keyboard control, terminate all running applications, sync cache data to the storage drives, unmount the file system safely, and instantly reboot the machine. It is the ultimate architectural emergency brake, providing absolute control over hardware state when software completely fails. Direct hardware poking via I/O subversion. The standard philosophy of modern operating systems dictates that user software must never talk directly to physical hardware components. Instead, applications must politely ask kernel drivers to handle the interaction. Linux contains two highly restricted system calls, ioperm and iopel, that completely shatter this foundational design principle. These commands allow a privileged user space program to alter the CPU's I/O privilege level for specific hardware ports. When granted, a standard script or application bypasses the entire kernel driver subsystem entirely. The software can then use raw CPU assembly instructions to read and write data directly to the physical input-output ports of attached hardware components, such as storage controllers, network interfaces, or motherboard chipsets. This capability completely strips away the protective abstraction layer provided by the OS. While incredibly dangerous because an incorrect write can permanently brick physical components or corrupt hardware firmware, it allows for total, unmediated control over the physical machine. It transforms the operating system from a strict, regulatory supervisor into a transparent window, exposing raw hardware registers directly to user control.